This time in the shop, let's talk about compromise antennas. Okay, today I want to talk about linear loading and inductive loading of antennas. And for this discussion, we're going to just limit our discussion to 10 meters because 10 meters is really the only practical antenna that you can put on an automobile where you can get a full quarter wavelength of antenna with no loading on it. So anyway, let's start out by modeling some antennas. This is just a vertical dipole. This is a vertical dipole. It's up about 10 feet off the ground. And being that it's a vertical dipole, the impedance should be about 70-ish ohms. It should have pretty good SWR, and it does. So where it's resonant, we can see it is 68-ish ohms. And let's go ahead and model it. And this is modeled above real ground, and we can see we have about 1.43 dBi, roughly. Now let's say that your installation requirements won't allow you to put up a full-size dipole like this. So what can you do? Well, you can bend the ends of the antenna. So let's look at an example where I just took the ends of that antenna and I bent them like so. So I bent them in the x-axis, but I bent them negative in the x-axis, and I did that for a reason, because I want to check the gain in the positive x-axis and see if we lose anything when we do this. So by bending them in the negative direction, there may be some gain in the negative direction, but we shouldn't see anything in the positive direction because it's bent away from the radiator. But let's see what we could do. We'll check the SWR, and you can see it covers a pretty good portion of 10 meters. Resonant about 28.6 megahertz, and when we plot it, you can see we have 0.94 dBi on one side, 0.9 on the other. So we did lose a little bit, but we lost roughly half of a dBi, which isn't much considering that this antenna is drastically shaped different than a standard vertical dipole. You can also see that the feed point is creative, and I'll explain that in a minute. But so we've bent these legs at more than the halfway point of this dipole, and we still have positive gain at 0.9 dBi. And if we check this as a three-dimensional plot, you can see it's perfectly omnidirectional. The pattern's not skewed hardly at all. So what's going on here? Well, to understand that, we have to look at our vertical dipole once again, and let's go ahead and model it once again. And the reason I wanted to do that is to show the current pattern on this antenna. And you can see the current is heaviest in the center of a dipole, and it's also very thin on the ends. So most of the radiating power in an antenna is in the middle of the antenna. The middle of the antenna does all the heavy lifting. The outsides of the antenna, not so much. And this is the reason that when you bend the legs of the antenna close to the outside of the antenna, it doesn't really affect the gain that much. It does, but not that much. And we call that linear loading. So this is a linear loaded dipole. And now we can talk about why the feed point is way down here in this bent leg instead of being in the center. In fact, let's move it to the center. Now we're back in the center. Let's go ahead and check the SWR on it. And now you can see why I moved the feed point, because the impedance is way low. It's 24 ohms. Double check that it truly is 24 ohms. Yes, 24 ohms. So the reason the impedance is so low is because we bent this at a 90-degree angle, and it's a significant portion of the radiator, and that will always drive the impedance lower. So when that happens, there's no reason, there's no law that says that you can't feed it from a different place than the center. The pattern will still be fine. It's just as we move it towards the outside of a leg, it's going to raise the impedance to the point where maybe we can get a really good match to a 50 ohm transmitter. So by moving the feed point of the antenna, you can just keep moving it down one leg until the impedance comes up to what you want, and you can see we're 49 ohms, really close to a 50 ohm match. And there is absolutely nothing wrong with that. Now, if you do get extremely far out on one leg like this, you probably want to run a common mode choke at the feed point. Because whenever you have a severely imbalanced antenna like this, you're going to get some common mode current, but nothing you can't deal with a common mode choke. Okay, so what's the purpose of discussing all this? Well, if you have a limited installation area and you can't get a dipole of any frequency to fit in that space, you can bend the ends of the dipole. Just make sure you bend them in the same direction, because if you bend them in opposite directions, you'll skew the pattern. But bend them in the same direction, bend them equally, and you could shorten it quite a bit, and it's not going to affect the gain that much. As you can see, we still have a pretty good antenna. Half a dB down from a full dipole, you're not going to see that on an S meter. That will be invisible on an S meter, and will be invisible to somebody listening to your signal. If you were switching it back and forth between a 1.4 dBi antenna and a 0.94 dBi antenna, they're not going to tell the difference. It'll sound the same. So these are, you would think that by bending the legs in this fashion, that you would make an antenna extremely skewed in pattern, but it's actually not the case. You see, we're purely omnidirectional. As long as you bend the legs in the same direction, you'll be fine. Now, limited space installations, you can get away with this, and the antenna will work just fine, but you may have to get creative on your feed point if it lowers your impedance to the point where it creates a problem matching to a 50 ohm transmitter. Now let's talk about the other limited space installation situation, which would be putting HF in your vehicle. So there's many ways to accomplish putting HF in a vehicle. Probably the most common would be just putting a quarter wave whip on the bumper, and this is the only way to get a quarter wave that I'm aware of in the HF spectrum on a vehicle, and you'll do that on 10 meters. 10 meters is about the only frequency you can do this with. Yeah, you may be able to do it on 20, and well, I guess you can do it on 6, but 6 is really VHF, not HF, so we won't even talk about 6 meters at this point. But so this would be a 10 meter quarter wavelength whip on a vehicle, and the radiation pattern of that antenna would look something like this. And you can see, if we can somehow take advantage of the bottom half of this waveform where the current is the strongest, this up here really doesn't matter too much. So there is a way to shorten that antenna, and the common way to do it is just by putting a loading coil at the base of the antenna. But if we put it at the base of the antenna, that's not the best place to put it, because if you put it at the base of the antenna, what you're canceling out is this section of the antenna down here. And you're leaving this portion up here where the current is lower. So base loaded antenna is not the best way to go. Let's get rid of that. If you're going to run a mobile antenna that's compromised, you want to run one that's center loaded. So by moving the coil up to the center of this antenna, you're taking advantage of this radiation pattern at the bottom of this antenna where it's strongest. So this part of the antenna is going to radiate very well. This part not so much. But it will combine in the far field to give you a decent pattern. This antenna could be 4 feet long, which would be half of a quarter wavelength on 10 meters, and it would operate just fine. You would notice very little loss in signal, and it would perform just fine. So that's why you'll see, well, you'll see both. You'll see center loaded and base loaded whips, but if you have a choice, center loaded is definitely the way to go. You will definitely not notice as much of signal loss with a center loaded antenna. And that's because this part of the antenna doesn't radiate very well. This part does. So center loading helps you to maintain that good section of antenna that you need. So there, I hope that helps. If you got any comments or questions, go ahead and throw them below, and I'll try and answer them as best I can. And as always, thanks for watching.